Did you know that fungus is actually an incredibly diverse life form that is astonishingly effective at computational tasks that even computers can't perform? Andrew Adamatsky discovered that slime mold can solve tasks of logic, arithmetics, solve mazes, computational geometry image processing, and even store memories. Slime molds can express their own unique form of creativity, generating novel and useful ideas. Mycorrhizal network, or CMN, is a natural network of fungus that spreads out in filaments through the soil of any given forest. These filaments connect the root systems of trees to each other all at once. These fungi also transfer information to each other that steers one another toward nutrient deposits in soil. The discovery of this information transfer led researchers to ask a bigger question. Is it possible to transform it into a tool and even harness it for computer processing? The leading role in fungal computing research is being conducted by a famously unconventional laboratory at the University of West England in Bristol, headed by laboratory director Andrew Adamatsky. They've proven that externally generated electrical signals to interface with the mycelial network makes them interact with each other. They can also generate signals that get the mycelia to send electrical pulses to electrodes and translate them into something practical on a classical computer. They can also evolve meaning from an engineering perspective by being applied into new types of computers with a high degree of flexibility. It turns out that there's all sorts of practical advantages of having a computer literally made of living material. They consume far less energy than a traditional computer, and being biodegradable can be disposed of without adding to the immense amount of harmful tech waste humans generate. They self-repair. They are resilient to electromagnetic pulses and can recover from issues that would cause system failure. A far cry from laptops and tablets today, whose processor can't survive a splash of water. This earned it the designation of a new tech category, wetware, which refers to the biological components of a computer system. Wetware, as opposed to hardware, manages to cross the gap between biological life forms and technology. This technology has allowed researchers to produce motherboards with actual mushrooms growing out of them. These motherboards consist of a meshed three-dimensional web of mycelium connections, acting as a root system that conducts electrical signals, which is received and passed along from a classical hardware source like a computer, before being passed along from the mycelium. The mushroom's fruiting body, which contains enough wetware to send and receive complex electrical signals, allow the fruiting body to serve as a form of RAM that allows the mushroom to keep data in the form of memory. These processes are dependent on the mushroom cell's ability to transfer electrical signals. This system enables a level of sophistication that is exponentially more complex than what today's computers can do. The mycelium's extensive and adaptive network allows for a form of parallel processing, where information can be analyzed simultaneously across the entire network. This makes fungal computers particularly suitable for tasks that involve large-scale data analysis. Mycelium networks have a lot of other advantages over regular computers. For example, if you stimulate it from at least 2 points, the conductive pathway for electricity to travel between those points produce stronger, faster-traveling signals that are much more reliable. Mycelia have unique shapes and structures, enabling them to carry out highly specified tasks according to their shape. Hypothetically speaking, these mycelial networks could conceivably be built into a fungal limitation of an animal brain in order to transmit directives. For now, the fungi are given the simpler task of interfacing with the signals sent within modern computer hardware and establishing the ability to communicate in a common language in the form of simple electrical pulses. Binary code is the Rosetta Stone of computer language. The presence of an electrical signal coming from the mycelium translates to half of a binary language for a computer, and absence of another signal is the other half of the binary. At this stage, the completed loop between fungi and motherboards are not particularly complex, and the goal as it stands now is to keep on providing proof of concept. Now that the bridge for organic fungal matter to communicate with electronics has been crossed, it's a matter of adding new capabilities and streamlining the process. One key overall distinction to make is that modern computers are unable to physically morph the way they work to solve new problems, and they're not able to truly learn in the way that a living being can. Mycelia change all of that by having those particular advantages when it comes to forming highly evolved neural networks. There are things that they hypothetically can't do very well that traditional computers can, and they need specific environmental conditions in order to function. Despite this, if we examine how fungi can be incorporated in our society, their potential value to humanity becomes very hard to ignore. Living fungal apparatuses have been shown to be able to respond to all sorts of physical stimuli coming from a human body, including chemical processes that current wearable technology is incapable of accounting for. They could become invaluable as wearable technology that actually understands your bodily processes, instead of merely taking a few readings and estimating the rest. That innovation alone would revolutionize the way that humans are able to monitor our own bodies and accommodate and respond to health crises, and much more. Fungal computers can also be incorporated into so-called smart building materials and everyday commercial and household technologies at exceptionally low cost, with hardly any environmental impact. Fungi have incredible potential to function as advanced sensors, processing the world around them in a way that no typical electronic sensor could hope to do, and again, surviving all manner of environmental challenges or stimuli that would render a modern sensor inoperable. It's impossible to know just how far the current work in fungal computing will ultimately lead. If one thing is certain, any large-scale adaptation of fungal computers will be a lot more complex than current technology. It will be an incredibly sophisticated fusion of technology with biology, creating something fundamentally different, and with any luck, fundamentally better than even the most stunning technologies we possess today.